Welcome to Numbers with Python. In this lecture, we'll discuss numbers, integers, floats, complex numbers, and binary, octal, and hexadecimal numbers. We'll also discuss various conversion functions and different modules that deal with numbers. You know what a number is? It is an arithmetic entity that lets us measure something. And since Python is dynamically typed, there's no need to specify the data type while declaring a variable. A is 798.321. Some numbers are integers. Say A is 7. An integer can be as long as you want. This only depends on the amount of memory you have available. A is an object of class int. A is not an instance of class bool. We can also work with exponential numbers in Python. 2 to the power 5 is the same as 2 lakhs point 0. Numbers can also have digits after the decimal. We call these floating point values. Let's import pi from the math module, print its value, and you get this. This is an object of class float. Although a number in Python can be however long you want it to be, floats are only accurate up to 15 decimal places. After that, they are rounded off. If A is this number and we print it, it rounds it off to 1.15 ones and 2. 2 by 2 gives us 1.0. Division always results in a float, even if it's only a 0 after the decimal point. Of course, Python has integers and floats, but it also has complex numbers. Such a number has real and imaginary parts and looks like A plus bj. J, not I. A is 2 plus 3j. Here, 2 is the real part and 3j is the imaginary part. The j is the complex coefficient. You can't use I like you learned in school. And can we do this? A is 2 plus j? No. This should be written as 2 plus 1j. A is 2 plus 3j. B is 2 plus 5j. If we add these, we get 4 plus 8j. This means the real parts get added together, and so do the imaginary parts. 2 plus 2 is 4, and 3j plus 5j is 8j. Now, A multiply and assign 2, and then print it. We can see it multiplies the real and imaginary parts by 2, and then prints the result. A decimal number is made of digits from 0 to 9. Python also supports other formats like binary, octal, and hexadecimal. Binary numbers can only be made of digits 0 and 1. They have prefixes 0b or 0 capital B. Octal numbers can contain digits 0 to 7 and have prefixes 0o or 0 capital O. Hexadecimal numbers may have digits from 0 to E. E here is 15, and these are a total of 16 digits, 0 to 9 and 8 to F. Hexadecimal numbers have prefixes 0x or 0 capital X. A binary number looks like this in Python. This is the binary for 7. Printing it and converting it into an integer results in the same thing. This is an octal for the number 8. The digit 8 does not exist in the octal number system. This is the octal for 9. This is the hexadecimal for 255. And this is for 254. Some functions let us convert one type of number into another. Int of 7 stays 7. Int of 7.7 becomes 7. The part after the decimal is truncated. You cannot convert a complex into an integer. Seriously, you cannot do it. This binary converts to 2, and this hexadecimal converts to 15. Let's convert numbers to float now. 110 becomes 110.0. 110.0 remains the same. You can't convert a complex into a float either. This is the octal for 8, which becomes 8.0. You cannot convert complex numbers into ints and floats, but you can convert ints and floats into complex numbers. 2 becomes 2 plus 0j, 2.3 becomes 2.3 plus 0j, and 2.3 plus 0j drops the decimal part. The bin function returns the binary equivalent of a number. Binary of 2 is 0b10. You cannot convert floats and complex numbers to binary. Oct returns the octal equivalent of a number. Oct of 8 gives 0 or 10, and you cannot convert a float into an octal. Hex does that for hexadecimals. 255 becomes 0xFS, and 0 becomes 0x0. Apart from the built-in types, Python also has some modules that help us deal with numbers. The decimal module helps with decimal fixed point and floating point arithmetic. Is 1.1 plus 2.2 equal to 3.3? Actually, not here in the Python interpreter. But why? Shouldn't they be equal? Let's see what 1.1 plus 2.2 gives us. Oh, well, this is due to hardware limitations. Since it stores decimals as binary fractions, it ends up doing it not very accurately. And what's 1 by 3? 0.33. So where does the decimal module come into picture? It lets us choose precision. The decimal function preserves significance. Let's import decimal. Here we call the decimal function with the value 0.1. To choose precision, we can set it this way. Now when we print the division of these two decimals, we get 0.0141. When we set the precision to 2 and then print it, we get 0.014. Precision tells us how well a number represents its decimals. The fractions module has the function fractions. This takes a number and returns the equivalent numerator and denominator. Let's import this function. Fraction of 1.5 is 3 by 2. We can also provide the numerator and denominator, and it gives us the resulting fractional number. Let's take one last module. For common mathematical functions like exponential, trigonometric, logarithmic, and factorial, we have the math module. Import math. Factorial of 5 is 5 into 4 into 3 into 2 into 1. This is 120. Exponent of 3 is e to the power 3. E is the mathematical constant. This is equal to 20.085. Finally, tan 90 is minus 1.995. Numbers are fundamental to numeric and scientific calculation. That's all for today.